the delayed choice quantum eraser. In 1999, physicists Yoon-Ho Kim and colleagues at the University of Maryland conducted an experiment that would fundamentally challenge our understanding of causality. The delayed choice quantum eraser experiment showed that a decision made in the present could retroactively change what happened in the past, not just our knowledge of the past, but the actual physical events themselves. The experiment works like this. Photons are sent through a double-slit apparatus, creating an interference pattern that proves the photons behaved as waves. But here's where it gets strange. The experimenters set up detectors that could determine which slit each photon passed through. But these detectors were activated only after the photons had already hit the screen and created the pattern. According to classical physics, this shouldn't matter. The photons already went through the slits, already hit the screen, already created the pattern. The decision to measure them afterward should be irrelevant. The photons had already completed their journey before any measurement was contemplated. But that's not what happened. When the experimenters looked at the data, they found something impossible. The photons that were later measured to determine their path showed no interference pattern, even though they had hit the screen before the measurement was made. The photons that weren't measured showed the interference pattern. The future measurement retroactively changed how the photons had behaved in the past. The experiment was designed with meticulous care to eliminate any possibility of the measurement apparatus somehow affecting the photons during their flight. The photons were already detected and recorded before the which path information was obtained. There was no physical mechanism by which the later measurement could have affected the earlier behavior, yet it did. Multiple laboratories have replicated this experiment with the same results. The photons somehow knew they would be measured in the future and changed their behavior accordingly. The cause, the measurement, came after the effect, the photon's behavior, but the cause still influenced the effect. Physicist John Wheeler, who originally proposed the thought experiment in 1978, said it proved that the past has no existence except as recorded in the present. The experiment suggests that the act of observation doesn't just reveal reality, it creates it, even retroactively. Wheeler went further, suggesting that quantum mechanics might mean the universe's entire history is not fixed until observed. The implications are staggering. If future measurements can change past events at the quantum level, what does that mean for causality, for free will, for the nature of time itself? Some physicists have argued this proves we live in a participatory universe, where observers play a fundamental role in creating reality, not just perceiving it. The Cornell Precognition Study. In 2011, Professor Daryl Bem of Cornell University published one of the most controversial psychology papers in decades. The paper, titled Feeling the Future, presented the results of 9 experiments involving over 1,000 participants that appeared to show humans could respond to events before they happened. Bem was not a fringe researcher. He was a respected social psychologist with decades of experience and numerous publications in mainstream journals. His decision to investigate precognition was itself controversial, but his rigorous methodology made the results impossible to dismiss easily. One experiment was particularly striking. Participants were shown 2 curtains on a computer screen and told that one curtain hid an image while the other hid nothing. Their task was to predict which curtain would contain the image. The catch: the computer didn't decide which curtain would contain the image until after the participant made their choice. The selection was controlled by a true random number generator based on quantum fluctuations, ensuring no predictable pattern existed. The image location was determined only after the participant clicked their choice, making any form of conventional prediction impossible. According to the laws of causality, participants should have performed at chance level, 50% accuracy. There was no information available to guide their decision because the outcome hadn't been determined yet. But that's not what happened. Participants correctly predicted the location of the image 53.1% of the time, a small but statistically significant deviation from chance. Over thousands of trials, this result was extremely unlikely to occur randomly. The probability of getting this result by chance was less than 1 in 100. Even more intriguing, the effect was stronger when the hidden images were emotionally arousing or erotic. Participants were better at predicting the location of provocative images than neutral ones. as if their future emotional response was reaching back in time to influence their present decision. This pattern, stronger effects with emotional content, appeared across multiple experiments. Bem's paper passed peer review and was published in the Journal of Personality and Social Psychology, one of psychology's most prestigious journals. The publication caused an uproar. Critics argued the results must be due to statistical artifacts or experimental errors. The paper sparked a crisis in psychology about publication bias and the reliability of p-values. Multiple researchers attempted to replicate the findings with mixed results. Some found similar effects, others didn't. The failures to replicate were widely publicized, while successful replications received less attention. This pattern itself became controversial. But in 2015, a meta-analysis examining 90 experiments by different researchers found a small but consistent precognition effect across studies. The data suggested something was happening, even if no one could explain what. The meta-analysis controlled for publication, bias, and methodological quality, and the effect remained. The standard scientific explanation is that random chance, publication bias, and subtle methodological flaws combine to create the appearance of precognition. But Bem and other researchers argue the effect is real and points to something strange about how consciousness interacts with time and probability. Bem has noted that if the effect sizes observed in precognition experiments appeared in any other area of psychology, they would be accepted without controversy. The presentiment experiments. Starting in the 1990s, researcher Dean Radin and colleagues at the Institute of Noetic Sciences conducted a series of experiments that appeared to show the human body responding to emotional stimuli before being exposed to them. These presentiment experiments measured physiological responses like heart rate, skin conductance, and pupil dilation. The protocol was simple. Participants sat in front of a computer screen wearing sensors to monitor their autonomic nervous system. At random intervals, the computer would display an image, either emotionally neutral, a chair, a landscape, or emotionally arousing, a violent scene, an erotic image. Researchers measured the participants' physiological responses continuously throughout the session. According to causality, physiological responses should occur after seeing the emotional image, not before. The body reacts to stimuli it has experienced. The sympathetic nervous system activates when we encounter something arousing or threatening. This is basic biology. But that's not what the data showed. Radin found that participants' bodies began showing stress responses approximately 3 to 5 seconds before the emotional images appeared on screen. Heart rate would increase, skin conductance would change, pupils would dilate, all before the computer had even selected which image to display, let alone shown it to the participant. The physiological response preceded the stimulus by a measurable amount of time. The effect was small but consistent across multiple studies involving thousands of trials. When the computer was about to display a disturbing image, participants' bodies showed stress responses in advance. When a neutral image was coming, no such response occurred. The body appeared to be sensing and reacting to an event that hadn't happened yet. Critics suggested the effect was due to timing artifacts, subtle cues in the experimental setup, or patterns in the supposedly random image selection. Maybe participants were unconsciously detecting patterns in the timing of emotional images. Maybe there were electromagnetic signals from the computer equipment that varied depending on the type of image being loaded. But Radin addressed these concerns in subsequent experiments, improving the randomization, using better physiological measurement equipment, and eliminating potential confounds. He used true random number generators based on quantum processes to select images. He isolated participants from any possible electromagnetic interference. He varied the timing intervals randomly. The effect persisted. Even more remarkably, similar experiments have been conducted by independent researchers using different methods and equipment. Experiments at the University of Amsterdam, the University of Edinburgh, and other institutions have found comparable effects. The presentiment phenomenon has been replicated across continents and decades. A 2012 meta-analysis examined 26 studies from 7 independent laboratories and found a consistent presentiment effect with odds against chance of more than 10 billion to 1. The effect size was small, the physiological changes were subtle, but the statistical significance was overwhelming. The standard explanation is that there must be some unidentified flaw in the methodology that all these experiments share, but no one has definitively identified what that flaw might be. The alternative explanation, that the body somehow senses future emotional states and responds in advance, violates everything we understand about causality and the nervous system. Some researchers have proposed that the presentiment effect might be related to quantum processes in the brain. If neurons exhibit quantum effects, and if quantum mechanics allows retrocausality, then perhaps the brain's quantum processes are responding to future states, but this remains highly speculative. The quantum Zeno effect reversal. The quantum Zeno effect is a well-established phenomenon in quantum mechanics, where repeatedly measuring a quantum system prevents it from changing state. It's named after Zeno's paradox about an arrow that can never reach its target if you divide time into infinitely small moments. If you measure a quantum particle frequently enough, it essentially freezes in place. The measurements prevent it from evolving. Each measurement collapses the wave function, resetting the system to its current state and preventing transitions to other states. This has been demonstrated in numerous experiments and is considered a fundamental feature of quantum mechanics. The effect has practical applications. It's used in quantum computing to stabilize qubits and in atomic clocks to maintain precision. It's a real, reproducible phenomenon that works exactly as quantum theory predicts. But in 2015, researchers at Washington University in St. Louis demonstrated something stranger, the anti-Zeno effect, where measurements could accelerate quantum transitions rather than prevent them. More intriguingly, they showed that measurements made after a particle had already changed state could retroactively affect how quickly the transition occurred. In the experiment, electrons in superconducting circuits were excited to higher energy states. Normally, an electron will decay back to its ground state at a predictable rate determined by fundamental physics. This decay rate can be calculated from quantum mechanics and should be independent of what happens after the decay occurs. By making measurements at specific intervals after the excitation, the researchers could change how quickly the electron had decayed, even though the decay had already happened before some of the measurements were made. The timing and nature of observations made after the decay affected the decay rate that had already occurred. The effect was subtle but measurable with their high-precision equipment. The timing and nature of later measurements influenced events that had already occurred. The researchers described it as the future measurements reaching back to affect the rate of past quantum transitions. They repeated the experiment hundreds of times with consistent results. This wasn't just about gaining information about what happened. The actual physical decay rate changed depending on future observations. Cause and effect were reversed. When they analyzed the statistics of decay times, they found patterns that shouldn't exist if the decay rate was determined only by past conditions. The paper was published in Physical Review Letters, one of the most prestigious physics journals, and has been cited extensively in quantum mechanics literature. The results have been independently verified by other research groups. Physicist Kater Murch, who led the study, was careful about the implications. We're showing that what you do in the future can affect what happens in the past. We're not talking about science fiction time travel, but in the quantum world, the relationship between cause and effect is not as simple as we thought. The experiment raises profound questions about the nature of time in quantum mechanics. If future measurements can influence past events, does the past actually exist as a fixed reality? Or is the past, like the future, somehow probabilistic and subject to modification by later observations? The flash crash precursors. On May 6, 2010, the U.S. stock market experienced what became known as the flash crash. In the span of just 36 minutes, the Dow Jones Industrial Average plunged nearly 1,000 points, about 9% of its value, before recovering most of the losses. Approximately $1 trillion in market value briefly evaporated. Some individual stocks traded at absurd prices. Accenture shares briefly fell from $40 to 1 cent. The crash was triggered by algorithmic trading programs responding to a large sell order of E-mini S&P 500 futures contracts placed by a mutual fund. The algorithms that dominate modern trading reacted to the order, which triggered more selling, creating a cascade that briefly overwhelmed the market. But here's what's strange. Analysis of trading data from that day revealed something that shouldn't be possible according to normal causality. Researchers analyzing high-frequency trading data noticed that certain trading algorithms began exhibiting unusual behavior approximately 200 milliseconds before the large sell order that triggered the crash. These algorithms started pulling out of the market, canceling orders, and adjusting positions as if they knew what was coming. 200 milliseconds might seem insignificant, but in high-frequency trading where computers make decisions in microseconds, it's an eternity. Modern trading algorithms can execute thousands of trades in that time frame. The algorithms change their behavior before the trigger event occurred, and in some cases, before the trigger event was even initiated by the trading system that would execute it. The data showed clear statistical patterns. Certain algorithms reduced their market exposure, widened their bid-ask spreads, and decreased their trading volume in the 200 milliseconds before the sell order hit the market. There was no apparent information available that would explain this behavior. The large order hadn't been transmitted yet. There were no news events, no obvious market signals. The SEC and CFTC conducted extensive investigations into the flash crash, but couldn't definitively explain why these algorithms acted in anticipation of an event that hadn't happened yet. The official explanation was that the algorithms detected subtle market microstructure changes that preceded the crash, essentially predicting it from early warning signs invisible to human observers. But some quantitative analysts have argued the timing doesn't support this explanation. The pattern changes occurred before any detectable market conditions that would predict a crash. Market volatility was normal, order flow was typical, liquidity metrics showed nothing unusual. It was as if the algorithms were responding to the crash itself, not to conditions that would cause the crash. Some researchers have suggested that in the microsecond world of algorithmic trading, where millions of transactions create a complex system with feedback loops, retrocausal effects might actually be observable. If consciousness or measurement can affect past quantum events, perhaps sufficiently complex computational systems interacting with market data, which itself may have quantum components in its generation, might exhibit similar effects. The phenomenon has been observed in other market events too. Analysis of the 2008 financial crisis, the 2013 bond market flash crash, and other major market disruptions has revealed similar patterns. Algorithms adjusting behavior slightly before trigger events with no apparent causal information available. The financial industry largely dismisses this as pattern recognition or coincidence. The algorithms are designed to detect subtle signals and may be responding to micro-patterns humans can't perceive. But a small number of researchers believe something stranger might be happening, that in the realm of high-frequency trading, where time intervals approach quantum scales and complexity reaches extreme levels, the normal flow of causality might break down. The reverse double-slit results. In 2007, physicists at the University of Vienna conducted a variation of the famous double-slit experiment that produced results challenging our understanding of when quantum wave function collapse occurs. In the standard double-slit experiment, particles shot at two slits create an interference pattern showing they traveled through both slits as waves. But if you measure which slit a particle goes through, the interference pattern disappears. The particle behaves like a particle, not a wave. This is the foundation of quantum mechanics. Observation affects reality. The Vienna team modified this by placing their measurement apparatus after the slits, but before the detection screen. They could choose to activate the measuring device or not after each particle had already passed through the slits. According to conventional understanding, the particle's behavior through the slits should be determined when it passes through, not by what happens afterward. The particle's fate should be sealed the moment it interacts with the slits, but the experiment showed otherwise. When the measurement device was activated, even after the particle had passed through the slits, no interference pattern formed. When it wasn't activated, the interference pattern appeared. The future decision to measure retroactively determined whether the particle went through both slits as a wave or one slit as a particle. The researchers used sophisticated timing equipment to track exactly when each decision was made and when each particle passed through the slits. The data was unambiguous. The decision to measure came after the particle had passed the slits, yet the decision still determined the particle's behavior at the slits. Even more strangely, by analyzing the timing with extremely precise instruments capable of measuring intervals down to femtoseconds, they found that the wave function appeared to collapse before the measurement was actually completed, as if the particle responded to the intention to measure, not the measurement itself. The collapse began approximately 50 femtoseconds before the measuring device finished its operation. The experiment has been replicated multiple times with consistent results. Different research groups using different equipment have found the same temporal anomalies. The implications are clear. At the quantum level, future events can influence past states. The effect precedes the cause. Physicist Anton Zeilinger, who led much of this research and would later win the Nobel Prize for his work on quantum mechanics, stated, "The distinction between reality and our knowledge of reality, between reality and information, cannot be made. In other words, what we choose to observe in the future creates what happened in the past. This raises profound philosophical questions. If the past is determined by future observations, is there really a fixed past? Does history exist in a definite state? Or is it, like quantum superposition, a collection of possibilities that don't resolve until observed?" The remote viewing anomaly. Between 1972 and 1995, the U.S. government funded a classified program investigating remote viewing, the purported ability to perceive distant locations through psychic means. The program was run by the CIA and Defense Intelligence Agency under various code names, including Stargate Project, Grill Flame, and Sunstreak. Over its 23-year existence, the program cost approximately $20 million and involved physicists, intelligence officers, and alleged psychic viewers. While most remote viewing results were inconclusive or ambiguous, one aspect of the research produced consistently anomalous data: retrocognitive trials, where viewers attempted to describe target locations that had been visited in the past or would be visited in the future. In a typical protocol developed by physicists Russell Targ and Harold Puthoff at Stanford Research Institute, a viewer would be asked to describe a location. Later, sometimes hours, sometimes days, a team member would randomly select and visit a target location from a pool of possibilities prepared in advance. The viewer's description, made before the target was selected, would then be compared to the actual target. The random selection process was carefully controlled using random number generators and sealed envelopes. The viewer had no normal means of knowing which location would be chosen. The selection happened after the description was provided. Statistically, these should match at chance level. The location hadn't been chosen yet when the description was made, but analysis of thousands of trials showed matching rates significantly above chance. Not dramatically so, but consistently enough that it couldn't be easily explained by coincidence. Independent judges who compared descriptions to targets found matches at rates around 65%, when chance would predict 50%. More intriguingly, the data suggested that trials where targets were visited further in the future sometimes produced better results than trials where targets were visited sooner. It was as if there was a temporal aperture, and distant future events were sometimes more accessible than near future ones. This pattern was unexpected and didn't fit any theoretical framework for how precognition might work. Some of the most compelling results came from coordinate remote viewing, where viewers were given only geographic coordinates and asked to describe what existed at that location. In several documented cases, viewers provided accurate details about locations they had never visited and which were selected only after their descriptions were recorded. When the program was declassified in 1995, the CIA released a statement saying remote viewing had not been proved useful for intelligence operations. The official assessment was that while some results appeared anomalous, they were not reliable enough for practical application. However, statistician Jessica Utz, who evaluated the program, concluded, "Using the standards applied to any other area of science, it is concluded that psychic functioning has been well established. The statistical results of the studies examined are far beyond what is expected by chance. Arguments that these results could be due to methodological flaws in the experiments are soundly refuted." The retrocognitive data was particularly puzzling. Even skeptical researchers acknowledged that the statistical anomalies existed. They just disagreed about what explained them. Ray Hyman, a psychologist and skeptic who also evaluated the program, acknowledged the statistical effects, but argued they must be due to some combination of subtle cueing and expectancy bias rather than genuine precognition. Could viewers really be perceiving events that hadn't happened yet? Were they unconsciously influencing the random selection process through some unknown mechanism? Or was there a methodological flaw no one had identified despite decades of refinement? The question remains unresolved. The Libet experiment reversal. In the 1980s, neuroscientist Benjamin Libet conducted experiments that seemed to show the brain initiating actions before conscious awareness of the decision to act. Participants were asked to flex their wrist whenever they felt like it and note the exact moment they became aware of deciding to act, using a fast-moving clock to mark the time. Libet found that brain activity associated with the movement, measured using electroencephalography, began about 550 milliseconds before the action, but conscious awareness of the decision occurred only 200 milliseconds before the action. This suggested the unconscious brain was making decisions before consciousness became aware of them, raising troubling questions about free will. The findings sparked decades of philosophical debate about whether we really have conscious control over our actions, or whether consciousness is merely observing decisions made unconsciously. But in 2011, researchers at the Bernstein Center for Computational Neuroscience in Berlin discovered something stranger. Using more sophisticated analysis of the brain signals and modern machine learning techniques, they found that conscious decisions could actually influence brain activity that had occurred earlier. When participants were allowed to veto their decision at the last moment, to consciously choose not to flex their wrist even after the decision process had begun, the brain activity patterns from seconds earlier would retroactively change when analyzed. It was as if the later conscious veto was reaching back in time to alter the earlier unconscious neural activity. The effects showed up in the data as statistical patterns that shouldn't exist if time flowed in only one direction. When researchers used machine learning algorithms to predict whether a participant would ultimately follow through with an action or veto it, they found that information about the final decision was somehow encoded in brain activity that occurred before the decision was consciously made. But the encoding changed depending on what the final conscious decision would be. More specifically, neural patterns recorded 2 seconds before an action looked different, depending on whether the participant would eventually veto the action or follow through with it. This information shouldn't exist yet. The conscious veto decision hadn't been made, but it was present in the earlier brain activity. The final conscious decision appeared to shape neural activity that preceded it. This suggests either that the brain is somehow predicting future conscious decisions with remarkable accuracy, or that the temporal relationship between conscious decisions and brain activity is more complex than we thought. Researcher John Dylan Haynes, who led the study, was cautious about the interpretation. We can't rule out that what we're seeing is a future conscious decision influencing past brain states. The data is consistent with that interpretation, even though it violates our assumptions about causality. What we're seeing suggests that the relationship between conscious decisions and brain activity might be bidirectional in time. The findings reignited debates about free will and determinism, but they also raised questions about whether consciousness operates according to the same temporal rules as physical matter. If consciousness exists outside the normal flow of time, or if it can access multiple time states simultaneously, it might explain both Libet's original findings and the retrocausal effects observed in the Berlin experiments. The quantum prediction market. In 2013, a group of physicists and economists created an experimental prediction market based on quantum mechanical principles. Instead of trading shares in conventional outcomes, participants traded in quantum states that could exist in superposition, simultaneously representing multiple possible futures. The market was designed to test whether quantum mechanics could improve prediction accuracy for complex events. Traditional prediction markets work by aggregating information from many participants, with prices reflecting collective beliefs about future outcomes. The quantum market extended this concept by allowing positions to exist in superposition until measured. Participants made trades based on their beliefs about future events, but the market itself operated on quantum computer hardware, where positions could exist in multiple states simultaneously until observed. When an event outcome was determined, the quantum positions collapsed into definite values. The strange result? The market appeared to know outcomes before they occurred with accuracy that exceeded classical prediction markets. When researchers analyzed the trading patterns, they found that the quantum states of the market shifted toward the correct outcome, an average of 3 hours before the events were determined. For events that had conventional information available, like election outcomes that could be predicted from polling data, the quantum market performed about as well as classical prediction markets. But for events that were fundamentally unpredictable, the quantum market showed anomalous accuracy. Even more remarkably, the effect was stronger for events that were fundamentally unpredictable, like random number generators or quantum measurements that would happen in the future. The market seemed to be sensing the actual future outcomes, not just predicting them from available information. The researchers tested this systematically. They created markets for quantum random number generator outcomes, numbers that would be generated by quantum processes, radioactive decay timing that are theoretically unpredictable. Classical prediction markets should perform at chance level for such events. But the quantum markets showed systematic bias toward the actual outcomes, with the bias appearing hours before the numbers were generated. The researchers ruled out information leakage. There was no way participants could have known the outcomes in advance because the outcomes were determined by quantum random number generators that hadn't fired yet. They also ruled out trading patterns or market manipulation, yet the market consistently moved toward the correct answer before it existed. The paper describing the results was published in Quantum Information Processing, but received little attention outside specialized quantum mechanics circles. The researchers themselves were cautious about the implications. We don't claim to have demonstrated retrocausality, but we have no conventional explanation for the observed correlations between present market states and future outcomes that are determined by quantum random processes. Some physicists have suggested the results might be explained by quantum entanglement between the trading system and the random number generators, creating correlations across time. Others have proposed that the many minds interpretation of quantum mechanics, where consciousness can access multiple quantum branches, might explain how traders' decisions could correlate with future random outcomes. The consciousness collapse timing. In 2019, researchers at the University of California conducted a series of experiments to determine exactly when quantum wave function collapse occurs. Using advanced timing equipment that could measure events at the femtosecond scale, quadrillionths of a second, they tracked the moment when a quantum system transitions from superposition to a definite state. The equipment used was at the cutting edge of what's possible in experimental physics. Femtosecond lasers and ultrafast detectors allowed them to track quantum events with unprecedented temporal resolution. The standard interpretation is that collapse occurs when a measurement is made, when a quantum system interacts with a measuring device in a way that records information about its state. But by measuring the precise timing of collapse events and comparing them to when measuring devices registered results, the researchers found something impossible. The collapse appeared to occur slightly before the measurement registered. We're talking about time differences of only a few femtoseconds, millionths of a billionth of a second. But in quantum mechanics, timing is everything. At these scales, the sequence of events matters fundamentally. The data showed that quantum systems were resolving from superposition into definite states approximately 7 femtoseconds before the measuring apparatus completed its measurement. The effect was small but reproducible across thousands of trials. They tested multiple quantum systems, photons, electrons, and atoms, superconducting circuits, and found the same temporal anomaly in each case. The quantum system somehow anticipated the measurement and collapsed just before it occurred. The cause, the measurement, came after the effect. The collapse. The researchers explored multiple explanations. Perhaps the measuring device was influencing the system earlier than they thought through electromagnetic fields or other interactions. Perhaps there were subtle electromagnetic effects propagating backward in time. Perhaps their timing equipment was miscalibrated or measuring something other than what they thought. But they systematically ruled out conventional explanations. They shielded the systems from electromagnetic interference. They calibrated their timing equipment against multiple independent standards. They varied the experimental setup in dozens of ways. The temporal anomaly persisted. The paper, published in Physical Review X, proposed that consciousness or observation might operate according to different temporal rules than physical causation. The act of observation might propagate backward in time through quantum entanglement, causing systems to collapse in anticipation of future measurements. The researchers suggested a model where the measurement event creates a backward propagating wave in spacetime that interferes with the quantum system before the measurement occurs. This would explain why the collapse precedes the measurement. The shadow of the future measurement reaches back to affect the present state. Other physicists remain skeptical, arguing there must be an experimental error or misinterpretation. But the data is clear. The effect precedes the cause by a measurable amount of time. Several research groups are now attempting to replicate these results with even more precise timing equipment. If confirmed, these findings would suggest that causality at the quantum level is fundamentally different from our everyday experience. The future doesn't just influence the present through normal causation, it might directly shape the past through quantum mechanical processes we don't yet understand. These 10 cases represent some of the most profound challenges to our understanding of causality ever documented. From quantum mechanics experiments showing particles responding to future measurements, to consciousness studies suggesting the brain can be influenced by decisions that haven't been made yet, to financial algorithms that seem to react to events before they occur. Some of these phenomena have conventional explanations. The delayed choice quantum eraser can be understood through the mathematics of quantum mechanics without necessarily invoking time travel. The presentiment experiments might be explained by unconscious pattern recognition or subtle experimental flaws. The flash crash precursors could be sophisticated prediction rather than precognition. But taken together, these cases paint a disturbing picture. Causality, the principle that effects follow causes, that the future cannot influence the past, might not be as absolute as we believe. At the quantum level, and possibly at the level of consciousness and complex systems, cause and effect might be more fluid than classical physics suggests. The implications are staggering. If effects can precede causes, what does that mean for free will? If future events can influence the past, is the past actually fixed? If consciousness can collapse wave functions before measurements are made, what is the relationship between mind and matter? Some physicists have proposed that retrocausality, effects propagating backward in time, is a fundamental feature of quantum mechanics that we've been misinterpreting. Others suggest that time itself might not flow in one direction at the quantum scale. A few argue that consciousness might operate outside normal temporal constraints. These aren't fringe theories proposed by pseudoscientists. These are peer-reviewed papers published in prestigious journals, experiments conducted at major universities, data analyzed by respected researchers. The scientific community is deeply divided about what these results mean. The standard response is that there must be errors or misinterpretations somewhere, but as these experiments are refined and replicated, the effects persist. The quantum eraser experiment has been reproduced in dozens of laboratories worldwide. The presentiment effect appears in meta-analyses of multiple independent studies. The timing anomalies in quantum collapse have been measured with increasing precision. What's clear is that the universe doesn't always behave the way our intuitions suggest. Cause and effect, the foundation of how we understand reality, may be more complicated than we ever imagined. At the edges of quantum mechanics, consciousness, and complex systems, the future might be reaching back to shape the past. Whether these phenomena represent genuine retrocausality, quantum mechanical effects we don't fully understand, or systematic errors in our experimental methods remains an open question. But one thing is certain, the boundary between cause and effect is far stranger than we thought.